Hey everybody, we're here today talking about how to construct polynomials using zeros. So we'll start with a fundamental theorem of algebra that tells us that an nth degree polynomial has n solutions over the complex numbers. And that's what we're going to be dealing with. You can restrict it to only dealing with the real numbers or integers or whatever numbers you really want. But we're going to look at all the solutions. So in this case, we're going to be looking for all n solutions. Alright, so let's take a look at the first example. Let's start off, pause the video, and think about what do you notice and what do you wonder. Okay, so you should be picking up on the fact that it's a degree 6. If we add up the degree of the different factors, right, we can see that we have 2 plus 3 plus 1. Okay, so it's a degree 6. The leading coefficient is going to be negative, and that goes with the end behavior of it, opening down, basically. Now, if we start to take a look at the zeros, right, we know that should correspond with the intercepts. So the 0x for x plus 6, set that equal to 0, x equals negative 6. And sure enough, we can see right there, there's our intercept. For the next one, x equals 0, well, we're done. Okay, and there we go, right? The origin is the intercept right there. Now the next one, x minus 5 equals 0, we get x equals 5 as our 0, so there's our intercept. It's a degree 6, it should have 6 solutions, but that doesn't mean it has 6 intercepts, as we can see. What's really going on is that we have what's called multiplicity. Okay, multiplicity. Okay, so this is the number of times that a number is a 0. So we can see that the degree of our binomial tells us the multiplicity. So x equals negative 6 is a 0 with multiplicity 2. And x equals 0 is a 0 with multiplicity 3. Multiplicity 1 is just, we don't really say that. We only talk about multiplicity when there's more than one. So we can see some interesting things. When we have an even multiplicity here for 2, it only touches the graph. It doesn't actually cross it. It touches it, but doesn't go through it. But then when we see we have an odd multiplicity, it actually goes through. Okay, but we have this squiggle here. All right, so that's interesting things there. Let's take a look at the next example. Right, here, graph represents a 6-degree polynomial. And we can see that we're told that f of negative 2 equals negative 3. So, well, we know that there should be a total of 6 solutions. Okay, so if we start with our intercepts, we can see there's an intercept here at x equals negative 8. We can see x equals negative 5 and x equals positive 1. Now, thinking about multiplicity from the last one, we saw that even multiplicity touch the x-axis. So this gives us an idea that this needs to be an even multiplicity, and that's going to be a multiplicity of 2 in this case. Because this one has an odd multiplicity, right? We could see a squiggle here as opposed to just going through, and so this has a multiplicity of 3. Okay, so when we start to construct our polynomial f of x, we're not quite sure what our leading coefficient is. Let's just call it a. Now we can start writing in our factors. We know for x equals negative 8, if we add 8 to make it equal to 0, we get x plus 8, right? So x plus 8 is one of our factors. Doing something similar, we have x plus 5 is another factor, but this one, we have to square it because that's a 0 twice. And then we're going to have x minus 1 with a cube. Okay. Now the added piece here is that f of negative 2 equals negative 3. So if we go ahead and plug that in, f of negative 2, right? Well, negative 2 plus 8 is going to be 6. Negative 2 plus 5 is 3. And then negative 2 minus 1 is negative 3. Okay. And so if we go ahead And now substitute. Right? F of negative 2 is negative 3. Right? We can actually start to solve for a here. Okay, so plugging this into the calculator, 6 times 3 squared times negative 3 cubed, it gives us negative 1,458. And so when we divide we're going to get 1 over 486. Okay, so we can go ahead and just go ahead and plug that, replace that right here for a, right? And we can check and see how that comes out. Okay, looks pretty good. Now, just to think about multiplicity and how that changes while we're here, I want to show you how this changes if we change the 2 to a 4. It still touches it, but it's elongated our graph. Where we have our cube, if we go back to a 1, a multiplicity of 1, okay, notice how, again, it just smoothly goes through, right? No squiggle or anything like that. But if we change it back to a 3, we start to get this squiggle. 5, and again, another squiggle, and we're starting to get our graph, elongated. Okay, so again, these different types of intersection points can give us an idea of what kind of multiplicity that we have, right? Whether it's a straight through, whether it touches, or whether we kind of have this squiggle going through, much like a general cubic. All right, last one. Okay, we want to find a fourth degree polynomial with a leading coefficient of 1/30 and the zeros of negative 3, 4, and 1 plus 2i. Okay. Now we know from the fundamental theorem of algebra this should have 4 solutions, but we're only given 3 of them. And this is where we need to use our knowledge about complex zeros. Okay, and that if a complex zero is one of our solutions, then its conjugate is also a solution. So the conjugate is just going to be the negative of the imaginary part. Okay, so 1 minus 2i is also our solution. So that tells us that we can start to create a polynomial. Let's call it g of x, okay, equals 1/30, because we know that's the leading coefficient. Okay, for our other zeros, we're going to have x plus 3 is that factor. For 4, the factor is x minus 4. Now, these ones start to get a little bit more complicated. We have x minus 1 plus 2i and x minus 1 minus 2i. Okay, and this is going to be difficult to put into a calculator, Desmos, or anything like that. So we're going to have to at least figure out what is this quadratic function that represents this one over here. Okay, so we can use the area model a couple times over here to see what's going on. Right, so we have x minus 1 minus 2i. I'm going to go and distribute, and then we have x minus 1 plus 2i. Okay, that represents our two situations here. Okay, so now we've got x squared, okay, negative x minus 2ix, and this is negative x plus 2ix, and then we have the product of these conjugates. Okay, well, let's go ahead and see what this is. We got negative 1 minus 2i, and then negative 1 plus 2i. Okay, negative 1 times negative 1 is 1. Here we've got 2i. Here we've got negative 2i. And then we have negative 4i squared. Okay, so we have some complex numbers to deal with here. Right? We know that I squared equals negative 1. Okay, so if this is negative 1, we've got negative 4 times negative 1, which is positive 4. Okay, 2i and negative 2i makes 0. And 1 is 1. So when we add this together, we get that the product of these two conjugates is just positive 5. Okay, all right, so we have 5 here. Now, we see the negative 2ix and the 2ix cancel. Negative x and negative x makes negative 2x. And we have x squared, right? So now we've got a polynomial, okay? 1 over 30 times x plus 3 times x minus 4 times x squared minus 2x plus 5. Okay. So one of the cool things is that if you do have complex numbers, you can write those two complex solutions, right? You can combine those together to form the quadratic that they come from, right? And so if we go ahead and take a look at Desmos from what we got, yeah, we can see right there, boom. We can see -3, there's our intercept right there, and +4 is our intercept. And our complex zeros are not actually going to show up as intercepts in the real plane. Okay, you'd have to do some more digging on complex numbers to understand that, but that's one of the reasons why we have to not just look for the intercepts, but we have to dig a little bit deeper. We know that there's going to be probably fewer intercepts than there are solutions, especially when the complex numbers are involved. So hopefully that gives you an idea of how to create these things, these polynomials using their zeros.